Hello and welcome to the lecture number 14 of Physics 401A. In this lecture, we discuss the motion of a particle under central potential. This will come, or rather this has come as a consequence of the reduction of a two-particle system moving under mutual interaction, under the effect of a potential which only depends upon their relative distance. And as you can just remember that in the last subpart of this lecture, we saw that under that effect of those type of potential, basically the problem of two mutually interacting particles was reduced to the motion of a single particle having the mass equal to the reduced mass of the system. Okay. So the equation, so the Lagrangian of the total motion, effective motion, can now be written as L is equal to half mu times r dot square minus u of r, where r is the relative distance between the two particles and mu is the reduced mass. Okay. Then basically we know that from our knowledge that ur can be written as a central potential, or just by differentiating u with respect to r, we can get a force field which is known as central force field, under which you can show that the torque of the total torque acting on the particle vanishes, and that's why the total angular momentum gets conserved in the system. And from that we can actually say that as the angular momentum, in general, the angular momentum by definition is always perpendicular to the position vector. Then if the angular momentum of the system is a constant vector, then constant vector, then in this case of central force, basically the position vector will be always perpendicular to a constant vector. That means the position vector will be always lying on a plane which is perpendicular to that constant vector. And that's why the conclusion basically comes that under a central force, the motion takes place effectively in one plane, and then we use directly 2D polar coordinates. But as I said in one of the previous lectures that basically while writing the Lagrangian, if you do not have any holonomic constraint, that means an equation involving coordinates and time directly, we cannot effectively reduce the number of degrees of freedom. Although we know that maybe the nature of the force, will basically constrain the motion in one dimension or two dimension, whatever, but in the Lagrangian we cannot, or rather we should not write that simplification. But in the most of the literatures, and I think in all of the very famous literatures, you always see that the simplification has been done from the first step. Here what I have tried to do, to start from the very general 3D Lagrangian of the system, and then just by using properties of Lagrangian and the Euler-Lagrange equations, we have to, I have showed that finally the basic motion or the effective motion takes place in one plane. So if you see that the Lagrangian can be written half mu r dot square minus ur, so just utilizing the symmetry of the potential term, we use spherical polar coordinates, which is three-dimensional spherical polar coordinates. So this r dot square will now have three components. R dot vector square will now have three components. It will simply be r dot square plus r square theta dot square plus r square sine square theta phi dot square times half of mu. That will give the total kinetic energy minus u of r. That is the Lagrangian. For simplicity, for the rest of the treatment, we will just use m, small m, for mu. Now we should write the corresponding Euler-Lagrange equations. We have three coordinates, three generalized coordinates, r, phi, r theta and phi. where r is this one. Okay, r is the distance from this point particle under interest from the origin. Theta is the angle between r and z, and phi is the angle between the the projection of r on xy plane with the x-axis. That is the traditional definition. Okay, for all the angles we try to take the orientation of the angles in the anti-clockwise direction. For example, here we take from r to z, here we take from x to phi. Okay, so from x to phi is also anti-clockwise if you see from the upward direction. Okay, that's just a matter of convention. You can just check whether which one is the most convenient for you. And if it is anti-clockwise, if it is just defined as it is in the picture, in our treatment we will consider that angle as positive, although we don't actually need here, basically just to clarify. Okay, so we write all the three Euler-Lagrange equations. The first one is d dt del L del r dot minus del L del r is equal to 0. That simply gives us the basic equation of motion in the radial direction. M r double dot minus m r theta dot square minus m r sine square theta phi dot square, which is equal to minus du dr. Right? Now these two are the Euler-Lagrange equations with respect to theta and phi. But remember, this does not say that this is the equation in the theta cap direction and this is the equation in the phi cap direction. That is not true. Okay. So if we just write this, we will have r theta double dot plus 2r dot theta dot minus r sine theta cos theta phi dot square is equal to 0. And again, for this one, from this one we can have m r square sine square theta phi dot is equal to constant. Basically, just by doing this you will see, and actually you can see directly from this expression of Lagrangian, that phi dot is present but phi is absent. So phi is a cyclic coordinate. So so that d dt of del L del phi dot will be equal to 0. Or there is a typo, that will be del L del phi and not del L del phi dot. Okay, so if phi is absent, this is 0, then d dt of del L del phi dot is also 0. So del L del phi dot is the conjugate momentum corresponding to the coordinate phi, and that will be simply equal to m r square sine square theta phi dot, that is equal to h. Now this is just a value which is conserved or constant of motion which we see in this motion. Now we even don't know whether this is the total angular momentum or a part of angular momentum or anything, but it is of course a part of angular momentum. That's for sure true just by checking the dimension, because m r square sine square theta phi dot has a dimension of m r square by t, so it is like an angular momentum. Now we directly try to calculate the total angular momentum of the particle, and we will see that what it gives. So the total angular momentum of the particle is calculated like this: r cross m dr dt vectorially. Now r vector is nothing but r scalar times r unit vector, right? R times r cap. So we can simply write d dt of r vector is nothing but d r scalar dt times r vector plus r d r unit vector dt. Of course, dr unit vector dt is non-zero because r unit vector, theta unit vector and phi unit vector, all of them are changing with time, unlike the unit vectors of Cartesian system which are fixed in time, right? So now you can easily write this one will be, so r vector cross r cap will be 0, so the only contribution comes from m r vector cross r dr unit vector dt. Okay, and this dr unit vector dt, if you do the calculation, you will see this is nothing but r times theta dot theta cap plus sine theta phi dot phi cap. That r I can take outside, So the total thing can be now written as a mod square r cap. Okay, so this r cap comes from this cross theta dot theta cap plus sine theta phi dot phi cap. Again, using that multiplication rule for the orthogonal coordinate system in the order of r theta phi, as you all know that r cross theta will be phi cap, theta cross phi cap, theta cap cross phi cap will be r cap, okay, and phi cap cross r cap will be theta cap. Okay, so r cap cross theta cap will be plus phi cap, and r cap cross phi cap will be minus theta cap, because phi cap cross r cap is theta cap. So if we obey this relation, then basically we can easily write a mod square theta dot times phi cap plus a mod square sine theta phi dot times minus theta cap. Okay. Now you see, till now, whenever we write this even in the form of in the term of theta cap and phi cap, we cannot still see a mod square sine square theta phi dot to appear. Here we have a mod square sine theta phi cap, but not sine square theta. So then we were just trying to see that what it gives in the Cartesian system. Okay, because we are just doing, investigating, okay, that how to get as a component of L this constant part, this constant value. We then write every unit vector over here, phi cap and theta cap, in terms of the Cartesian coordinate system. In case of the Cartesian, in terms of the Cartesian unit vectors. Then you will have a mod square theta dot minus sine phi I cap plus cos phi j cap minus, you will have a minus over here that will come here. So minus a mod square sine theta phi dot times cos theta cos phi I cap plus cos theta sine phi j cap minus sine theta k cap. Okay, these are all very simple algebra and they are very much doable. You can also check that at home. They are very good exercises. Okay. So if you do that, you will see at the end of the day you will have, and then you just you just group in terms of I cap, j cap and k cap. You will see that along I cap or the normal x direction, you will have a mod square within bracket minus theta dot sine phi minus phi dot sine theta cos phi. Okay, along j cap or y direction, you have plus a mod square within bracket theta dot cos phi minus sine theta cos theta sine phi times phi dot. And finally, you will have along k a mod square sine square theta phi dot. Voila! You finally can see that this constant factor comes here. And look, this constant factor is also directed along a unit vector which is also constant, right? So that means that the z component of L basically is a conserved quantity, not the total L but the z component of L. Now we can actually try to see that can we somehow transfer the coordinate systems in such a way that our total angular momentum will now be just directed along the z direction. So if you really remember, the basic reason of having an angular momentum is the rotation. Okay, so the question is that can you think that all the effect of rotation can be supposed to be just along z direction? Or the question can be put in another way, that if we even can do that, will the physics be unchanged? Well, as you know that we can easily do that just by changing suitably the coordinate axis by rotation, by a suitable rotation. So your L basically has this direction, which has some I component, some j cap some x component, y component and z component. Now let us rotate the vector in such a fashion that it will only have this k component and both of these components will vanish. Okay. But the question is that under such type of rotation, will the Lagrangian be invariant, or will the Lagrangian, if it is invariant, then we can say that the basic dynamics can be invariant, because according to our framework, if the Lagrangian is invariant or having a symmetric transformation, the motion or the analysis of motion would not change, right? Before coming to that point, just let me mention that the Lagrangian will not change by value, that's for sure true, because we are always writing the same terms, okay. But the functional form can change from L to L prime, okay. So if you just do the, if you just rotate the coordinate axis, basically, then just by writing some terms, okay, that will be now, it will simply be a point transformation, okay. So rotating a coordinate axis by some angle will be just a point transformation, right? So the new Lagrangian now, when will be written in terms of the new variables of the new rotated coordinate axis, their functional form may change, okay, but they will be the same Lagrangian, okay, there is no problem, because you are writing the same expression in terms of the new coordinates, right? And L prime, as you already have seen in one of the tutorial problems, that L prime will also satisfy Euler-Lagrange equations with respect to the new variables, right? But that is something to just tell you. Now coming to our previous question, that under the rotation, will the Lagrangian be invariant? Well, the Lagrangian in 11 is evidently invariant under rotation. Why? Because it simply, if you just see this form, okay, if you just see this one, this Lagrangian basically involves the mod of a vector, mod square, right? So this is the mod square of r vector dot, right? And you know that under a rotation of coordinate axis, the mod of any vector will never change, and this is also depending on the mod of r vector, so that will also be unchanged. So that is the gift we have when we talk about the central force, because we have the central force type of potential, so the Lagrangian basically can be, remains unchanged even after the rotation, and so that by changing little, or by without changing the physics, we basically say that the total, the direction of the total angular momentum can be set to the z-axis. So basically we can say that after the rotation, our system will be such a system for which the total angular momentum is a constant vector. And now you can easily think that what you can prove from Newton's law of force, that means the r cross f is equal to 0, so the torque is 0, so the angular momentum is conserved, here comes as an outcome of rotational invariance, right? Okay, so now what is the outcome for that? So if it is now directed, the total L is directed along Z, then we necessarily should have Lx is equal to 0 and Ly is equal to 0, right? So what we will just see that under this situation, what will be the restrictions on our previous coordinates theta phi, okay? We of course there is always a possibility. So if you just see Lx and Ly, the x and y components, they are m r square times these angular parts, okay? Now you can always say that the x component and the y component, they are 0 if r is 0, but if r is 0, the z component is also 0, then the total angular momentum is vanishing also. So this is a trivial case, this is not of our interest. We will try to see when r not equal to 0, then the individual contributions within the brackets, they will vanish. So you will have minus sine phi theta dot minus sine theta cos phi dot is equal to 0, and you also have cos phi theta dot minus sine theta cos theta sine phi dot is equal to 0. Okay. If you just combine this both relations just by multiplying sine phi with this and cos phi with this and subtract equation number 16 from equation number 17, you will see you will simply have cos square phi plus sine square phi times theta dot is equal to 0, because both of these terms will then cancel each other, right? And you will have, that means theta dot is equal to 0. This is a very important conclusion. So theta dot is 0, so theta is constant. So under this, after this rotation of the coordinate axis, we are in such an orientation where the total angular momentum is constant and directed along z direction. The theta is constant. So what is the meaning of theta constant in general? Now you just think in terms of the spherical polar coordinate system. So theta constant simply says here that it will be a plane, okay, it will be a plane with a given co-latitude. That means that plane can be slant, that plane that can be a plane like which can be simply the xy plane, or several planes which can cut the xy plane, normal xy plane, along the x-axis. Okay, if you just rotate the xy plane along x-axis, then you will have different planes with constant theta, right? Just a minute. So coming back to this, okay, so we still don't know that which one. So theta is constant is okay. Can we also say more about theta? That means should theta have any constant value or some specific value? For that we now use, you say that we are only using the Lagrange properties and Euler-Lagrange equations. We now use this equation with the Euler-Lagrange equation with respect to theta. Okay. So this one, equation number 13, this one now gives us r theta double dot plus 2r dot theta dot minus r sine theta cos theta phi dot square is equal to 0. If your theta is constant, then both theta dot and theta double dot is 0, and you will have this one is equal to 0. Again, r is not equal to 0 for the reason said before. You now have sine 2 theta phi dot square is equal to 0. Again, phi dot cannot be 0, because if phi dot is 0, then the total angular momentum which we have now fixed, that will be vanishing because phi dot is there. So phi dot cannot be 0. What about sine 2 theta? Can sine 2 theta be 0? Well, sine 2 theta can be 0 if theta is equal to 0 and pi by 2, right? In the framework of spherical polar coordinates, only those two angles are possible, right? Because if 0, that will be sine 0 0, otherwise sine pi will be also 0, sine 180 degree, right? Now if sine 0 is sine theta is 0, I mean if theta is 0, again we have a problem because sine square theta is 0, so again this is 0. So the only possibility is that theta is 90, right? So sine 2 theta is 0, but sine square theta is 1. Then you have this one is just equal to mr square phi dot. Okay, and what is that? That means this is simply the normal xy plane. Simply the normal xy plane. So the motion is now taking place on xy plane, and the momentum, I mean angular momentum, total angular momentum is directed along z-axis, and it is a constant. Okay, so now using all this knowledge, finally you can write, or rather you can reduce rigorously this Lagrangian using theta is equal to constant. So this will be 0 and sine square theta is equal to 1. So you have half m r dot square plus r square phi dot square minus u of r. So you see this is a reduced Lagrangian. This is not a Lagrangian which should be written from the beginning. Although in all the literatures, all the usual literatures I have seen, they have started right from the beginning this type of assumption. Okay. So this is a rigorous demonstration. Okay. And when you have this, then you can say again, you can observe that phi is a cyclic coordinate. Okay, the cyclic nature of the phi is of course always there, and so del L del phi dot, this is the only component of angular momentum for this case, because only one angle is there, and that will simply be m r square phi dot is a constant of motion, right? So finally, if we just write del L del phi is equal to a constant of motion is equal to h, then m r square phi dot will be equal to h. So phi dot can be replaced by h by r square, or rather h by m r square. Okay. Now try to understand, this is not a holonomic constant. Okay. Even if I just give you that you have a Lagrangian and I give you from the beginning that look, this is your constant. Is it a holonomic constant? No, because this is a function, this is an equation between r and phi dot, not r and phi. Okay. So somehow the generalized velocity corresponding to phi interferes. So this is a non-holonomic constant. Okay. So you see that finally using this one, effectively you can somehow write those equations after having, after reducing the Lagrangian and after solving the Euler-Lagrange equations for phi, you can write the Lagrangian in this simplified form. But directly from the beginning, just by using that, you cannot reduce phi in, or rather phi dot in terms of r. This is my, this is what I was trying to say about holonomic constants. Okay. Now you have solved this, and you have solved the Euler-Lagrange equation for phi, and you have this simplified form of L half m r dot square plus h square by m square r square minus u of r. So you only have r dot and r. So this is a Lagrangian. This is a Lagrangian which is of effectively one dimension. This is not a true one-dimensional Lagrangian. This is an effectively one-dimensional Lagrangian. Why it is an effective Lagrangian? Okay. Now let me tell you that if it is just, if it is just a true one-dimensional Lagrangian, then what would be your conclusion about T minus V? Because this is a Lagrangian where the total energy, this is, a conservative system because U is there and U is just a function of R. So this is a conservative system. So T minus U should be there. So if you write T minus U, what should be your T? Of course, half m r dot square. So this will be your then the contribution for the kinetic energy. Then you say that the rest of that part will be the potential energy, and that will be your effectively your U. So your U will be, U effective will be half m h square by m square r square. That means h square by 2m r square with a minus sign plus U, right? So your U effective will be U minus h square by 2m r square, right? Now, since the Lagrangian is not explicitly time dependent, we can also show that E, which is this time type, this term, summation over qi dot del L del qi dot minus L, this is also a constant of motion. If you calculate that, and actually you can show that explicitly. If you calculate that, you will see that E is equal to this. Now remember, now you can say that this is always your kinetic energy, and what is your potential energy? Potential energy is h square by 2m r square plus u of r. So here your potential energy was h square by 2m r square, u minus h square by 2m r square. Here you have u plus, u minus h square by 2m r square. Here you have u plus h square by 2m r square. So they are not mutually consistent. That is only because this is not a true one-dimensional problem. Okay. But I mean, if one says that what is the effective potential energy, actually you have the freedom to say either it is U minus h square by 2m r square. If you think that your reference of argument will be Lagrangian, or if your reference of argument will be E, then you can say my effective potential energy is U plus h square by 2m r square. Okay. Whatever be, finally the good news is that you have an equation just having r dot and r. So you can simply write r dot will be equal to root over 2 by m e minus u minus h square by m square r square. And you can solve for t, just according to the prescription which we discussed in the lecture number 12. Okay. Of course, you have to know the basic functional form of u for that. If you are, of course, if you know how to integrate that correctly, then you can solve for t. And then again, doing the inverse transform, okay, you can have r as a function of t. Okay. The same thing will be there. Phi dot is equal to d phi dt, which is nothing but now h by m r square, right? And then you can say d phi will be equal to h times dt by m r square. Now dt you can write in terms of dr by root over 2 by m e minus u minus h square by m square r square. So d phi will simply be this is the form of dt times h by m r square. And if you integrate, finally you will have a relation between phi and r. And what is this? If you remember, when you did in the in the central force motion under central force using Newtonian framework, basically the relation between r and phi gives you the equation of the orbits or the trajectories, right? So that's super important, having this relation. Now I already had made a mistake, you can see. So as I can say that, so from the expression of E, basically, the resulting motion can be regarded as a one-dimensional motion under the influence of an effective potential energy U plus h square by 2m r square. If it were Lagrangian, it were just U minus h square by 2m r square. Okay. This extra term is known as centrifugal potential energy. Okay. Now the value for which R corresponds to zero kinetic energy is called RC. Okay, just you can call it RC. We call. Okay, there is no reason for that. Some critical R or something. Okay, that means the total kinetic energy is zero, and your U will be equal to E. And what is the meaning of that? This is zero. Okay, R dot is zero, and RC is infinity. Okay. So that you can easily understand, only at infinity basically you can have that particle should have a total kinetic energy will be at zero. Okay. Then there is another interesting value of R is equal to R star, where only R dot is equal to 0. And if R dot is equal to 0, so in your effective one-dimensional problem, it may look like a system where the kinetic energy vanishes. But you have to remember that the particle is not at rest, simply because its cross-radial component of velocity is still alive, right? So it simply indicates the point where R begins to decrease after increasing, okay, for a while, and vice versa. That means let's say R was increasing increasing in some according to some trajectory. So at this point, R will stop increasing and begin to decrease. And if it was decreasing from some point, it will stop decreasing, it will begin to increase. Okay, so it changes its nature of change actually. Okay, so these are the turning points. Okay, if you just see this type of picture, you will see. So here, for example, when the particle is going from here to here, so the R is basically increasing. So R basically measured from this center to this direction. Okay, so basically you can see that the position vectors are increasing. Then this is the turning point, and after that when it comes back, basically r is decreasing. So that is the question. So at this point it basically changes. Okay, changes the direction of his motion or something. But at this point it is not at rest. That's what I am saying. But the total velocity is in the tangential direction. Okay, it's only due to phi dot. Now let us also try to make a correspondence. That was the correspondence of turning points between this true one-dimensional problem and the effective one-dimensional problem. So for true one-dimensional problem, really the particles, really they come at rest at turning points. Okay, here it is no. Now we are talking about also what is the correspondence of infinite and bounded or finite motions. So if for such systems R has only a lower bound, that means only we have R greater than or equal to some R of minimum, R minimum, but we don't have any value of R should be less than equal to R max, then the motion is infinite. That means the particle can come from infinity, can go to infinity, right? That is simply because while increasing the R, okay, the particle should not face any turning point where R dot equal to 0. Okay. Now if you have for a system, okay, R mean less than equal to R, less than equal to R max, that means R is within R mean and R max, then the motion is finite and the path lies entirely within the annulus between the circles R is equal to R max and R is equal to R mean. That is simply here. You can see the very small circle. This is the circle of R mean and that is the circle of R max, and all the motions are in between. Okay. However, it does not mean that the path should be a closed curve. If the radius vector R turns through an angle delta phi in times delta t, that is the time required for R to go from R max to R mean and back. So that means, let's say it starts from here, that point, okay. Then it, okay. Let me just choose this, okay. It starts from here and then it just go along this curve in this direction, okay, up to this, okay. So, and then finally it actually I can easily use this. It starts from this, then along this it just go like this, and so you can actually see by this red it's position vector, no? That's great. So when it comes back really again to R mean, okay, or rather you can easily say that the particle may be starting from here and go like along this position and then go and then this again come back to this point again, okay. So in order that the orbit or its path should be closed, it should come back to the original point. So in terms of the angle subtended over here by these position vectors, that must be a perfect multiple of 2 pi without any fault, right? And of course, between those, we have to make full trips. That means our mean should come to R mean again, right? So if we just say that for one full trip, we can write the angle subtended by the position vector is delta phi, then this will be 2 times integration from R mean to R max h dr by m r square root over 2 by m e minus u minus h square by m square r square, or by simplifying you simply write integration 2 times integration h dr by r square root over 2m e minus u minus h square by r square. This is just nothing but coming from this integration. Okay. Now remember, I have used here 2 just by saying that we assume that the symmetric motion between R max and R mean, because there is no dissipation. Okay. So if you have this, then this is the time, this is the angle subtended at the center by the position vector, and let's say after some m trips, n full trips, after n full trips, sorry, after n full trips, okay, the angle traversed should be a perfect multiple of 2 pi. That means n times delta phi will be equal to 2 pi times m. If that is satisfied, then only we can say that the orbit is closed, right? Then delta phi will simply be m by n times 2 pi. Now remember, there can be several examples where basically the 2 pi angle can be subtended in the center, but the one full trip is not yet over. That is also possible, right? If basically the position vector, let's say, starts from here and then first increases, just a minute, the position vector, let's say, starts from here and then first increases, and then without decreasing it again goes here, increasing, again increasing, and after such things finally it decides to decrease. Okay, this is also possible. Okay, in some, under some force law, maybe it is possible. I mean, we cannot say this is impossible. That is the thing. Then what happens? Then and by that time, more than one 2 pi angle is traversed over here, but this is only one trip. Okay, so that's why we have said that n full trips should be equal to m times 2 pi. Just think about this. Okay, now, so this is the condition for having a closed orbit. If m by n is a rational fraction, then only we can have. If it's like root 2, or again it is like a pi, then it is not possible, because pi is also irrational, right? Okay, there is an important or interesting theorem that there are only two types of central fields who lead to all the finite motions under this field to be always in closed orbit or paths. So one is that if the potential field is 1 by r, that is the Kepler problem, normal like electrostatic Coulomb potential or gravitational potential, or ur is a function of r square, that is the simple harmonic potential. Okay, if we have potential of this type of function, then the thing is that all the finite motions must have closed orbit. That's a very powerful and elegant theorem. We are not going in the scope of this course the detailed derivation of Bertrand's theorem. You can see in the books or on the internet. Okay. Now, just 2 or 3 points to remember. First point, remember r dot is equal to dr dt, which was root over 2 by m e minus u minus h square by m square r square. Now, at turning points, r dot, basically exactly at turning point, r dot is 0. So basically, just after the time, at the turning point, it should change its sign. Before and after the turning point, the signs are different. And if you remember, this integral also appears in the expression for both for t and for phi, the same integral. Okay, so if this integral changes this sign, the total thing under the square root, basically that will be the that will also make the angle phi and the time to change its sign before and after the turning point. So that's why we say that if the angle phi is measured from the turning point to the direction of position vector, or from the position vector to the turning point, okay, then for each values of r, the angle subtended to the two sides of the turning point direction is equal. That means with respect to the turning point direction, the two segments, that is from coming to r minimum to r maximum, and for going from r maximum to r minimum, is symmetric with respect to both angles and time. Okay, that is the thing. Okay, another interesting point, and that is the last interesting point for this lecture. Okay, in the presence of centrifugal potential, when we have H not equal to 0, it becomes more and more difficult for a particle to reach the center of the field, as H square by 2m r square tends to infinity, actually positive infinity, because H square by 2m r square is always positive definite, as r tends to 0. Okay, what is the meaning of that? That means when ur is of repulsive nature, then already ur tries to prevent the particle from coming to the center of the force, because there is no, the particle just see that when it just approaches to the center of the force or the center of the potential, whatever, it energy increases, right? And that's why it doesn't want to go there, because it always tries to, its potential energy increases, so it always tries to go to minimize its potential energy, right? Now when it has an attractive potential, for example, the ur part is attractive, because ur part can be repulsive or attractive. When it's attractive potential, then it has a negative contribution, so it then when the particle basically approaches towards the center, due to ur, its potential energy, due to the nature of ur, its potential energy basically decreases. And if ur were alone, then basically the particle would have negative infinite energy at the center. So center would be its absolute stable equilibrium point, and the particle would definitely fall into the center. Now, as a result of having H square by 2m r square as a positive definite quantity, okay, even when we have an attractive potential, this is not guaranteed. Okay. So as I said here, the fall to the center is possible only when ur tends to minus infinity sufficiently rapidly, dominating H square by 2m r square as r tends to 0. And we now have, from the expression of total energy, that is half m r dot square, which is the kinetic energy, just the radial part of the kinetic energy, is equal to E minus ur minus the centrifugal potential part. And that must be equal to, must be greater than 0. That because half m r dot square is always a positive definite quantity. Okay. Then you can say r square ur plus h square by 2m less than er square. I am just multiplying everything by r square. Okay. Now at r tending to 0, you can simply say E is a constant, so E times r square will be tending to 0, so you just make it 0 in the limiting sense. And then you can say this condition then boils down to r square ur less than, there will be a minus sign in your note, just check it and edit it, minus h square by 2m. Okay. So u of r must tend to minus infinity either as minus alpha by r square. Okay. If ur is just minus alpha by r square, having alpha is a positive quantity, then what happens? Basically r square cancels out, and your minus alpha will then be less than minus h square by 2m with alpha greater than h square by 2m. Right? That is exactly the same thing whether we are writing minus alpha less than minus h square by 2m or alpha greater than h square by 2m. That is correct. Okay, that is one possibility. Or you are simply can decrease with r with a steeper power law. That means you are simply can changes as r like 1 by r to the power n with n greater than 2. Okay, so if either of this situation arises, then only the domination, or rather the effect of the centrifugal potential is subdued in the vicinity of the center. Okay, and the particle would fall in the center. Okay, thank you very much.